All right. So energy and heat. Heat is closely related to temperature, but temperature is just a measure of how hot or how cold something is. Heat, on the other hand, has a direction, a movement of energy. So let's get to the notes here. It says, all chemical reactions are accompanied by a change in energy. Energy is defined as the capacity to do work or supply heat. So energy can actually do work or supply heat. So in this instance, I'm talking about energy in the form of heat, supplying heat. There are two kinds of energy, by the way. You may have heard of them. The first one is potential energy. This is stored energy. Examples of potential energy, I'll give you several. A rock on the top of a hill certainly has a lot of potential energy. Another example, a coiled spring. That's if you take a spring and like you push it. So it's like a wound up or a coiled spring. It has a lot of potential energy. Water behind a dam, potential energy example. So you get the idea. The energy is being stored. It's ready to just burst out into kinetic energy. Kinetic energy is number 2. Kinetic energy is the energy of motion. So potential energy, stored energy. Kinetic energy, energy of motion. Now, potential energy and kinetic energy are interchangeable, right? I can push that rock down the hill, the spring can uncoil, and I can lower the dam to release all the water. Now, in chemical reactions, stored energy, or potential energy, in the reacting compounds, that can get converted into heat. All right? Now, heat, I'm finally going to define heat for you. Recognize that its definition is different than temperatures. Heat is the kinetic energy of moving particles. All right? And these particles are moving, and they're moving in one direction or another. Now, the SI unit for energy is something called the joule. Okay? Joule, capital J. But the metric unit is often used quite a bit as well, and that is the calorie, C-A-L-O-R-I-E, abbreviated C-A-L. All right? It's a conversion factor here is 1 calorie is equal to 4.184 joules. So that's taken to be exact. Okay, that's an exact number. All conversion factors are exact numbers. So 1 calorie is equal to the amount of heat required to raise the temperature of a substance by 1 degree Celsius. I'm sorry, the amount of heat required to raise the temperature of 1 gram, and it's not just any substance, it's 1 gram of water by 1 degree Celsius, my bad. So 1 calorie, just to reiterate, 1 calorie is equal to the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And that's also equal to 4.184 joules. Now, not all substances, water, for example, versus copper versus iron, have their temperatures raised to the same extent when equal amounts of heat are applied. For example, if I boil water on a stove, right, the pan gets a lot hotter, a lot quicker than the water that's being boiled, right? As you warm up the heat, the pot gets hot real quick, but the water doesn't. Water is really good at being what's known as a coolant, and we'll get that. We may get back to that in a bit. But first things first, let's stick to our notes here so I don't get off topic. Not all substances have their temperatures raised to the same extent when equal amounts of heat are added. Next bullet point, the amount of heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius or Kelvin is that substance's specific heat capacity. Specific heat capacity has units of joules per gram per Celsius. For aluminum, specific heat capacity is 0.897 joules per gram per degree Celsius. That means it takes 0.897 joules of energy to raise 1 gram of aluminum by 1 degree Celsius. Copper is 0.385, doesn't take as much heat. Copper gets hotter quicker. Iron, 0.452, joules per gram per Celsius. Now look at water, way, way, way bigger, 4.184 joules per gram per degree Celsius. So metals, aluminum, copper, and iron, they don't require as much heat to raise the temperature of 1 gram by 1 degree Celsius. As a result, they get hotter quicker. Okay? Water requires a lot of heat. It can take in a lot of heat before it raises its temperature by 1 degree for 1 gram of water. All right, so let's take that further and put it into an equation for heat gain or heat loss by a substance. Okay? So heat gain or heat loss is measured in joules. That's why you see the capital J in parentheses. And that is equal to the heat gain or lost by a substance is equal to the mass of that substance in grams times that substance's specific heat capacity in joules per gram per Celsius times the temperature change. Now the temperature change is the final temperature, TF, minus the initial temperature, TI. So we have an equation here, right? Now I've put in words here, but the equation drills down into something very, very simple. Q equals MC delta T. Q equals MCAT, right? Try to remember that. Q equals MCAT. So what's the specific heat of aluminum? This is an example. What's the specific heat of aluminum if it takes 161 calories to raise the temperature of a 75 gram sample of aluminum from 12 degrees Celsius to 22 degrees Celsius? So we have 161 calories is required to raise the temperature of a 75 gram sample from 12 degrees to 22. So Q equals MCAT. Q equals MC delta T. In other words, Q equals MC times TF minus TI. Let's just plug numbers in. If it's one equation, we should be down to one unknown in order for us to solve it. 161 calories equals 75 grams times C, our unknown, our specific heat. Specific heat's the same thing as specific heat capacity, times 22 minus 12. So when you do the math here, you get a specific heat for aluminum of 0.21 calories per gram per degree Celsius. Not joules in this instance because they gave us the heat in calories instead of joules. All right, question 40B. Use the heat equation, that's the Q equals MSAT, by the way, Q equals MS delta T. Use the heat equation to calculate the energy in joules required to heat 75 grams of water from 22 degrees Celsius to 66 degrees Celsius. All right, as I stated earlier, the heat equation is Q equals MS delta T. M is mass, S is specific heat, and delta T is T final minus T initial. Q is heat. So the Q equals 75 grams of water times the specific heat capacity of water, 4.184 joules per gram per Celsius. Now the specific heat of water is also 1 calorie per gram per Celsius, but we use the 4.184 joules here because they want us to solve for joules. I get a Q equals 13,807.2, but I have to put it in 2 sig figs, so it's 14,000 joules. Why 2 sig figs? Well, 75 grams of water for one. All right, 41D, calculate the energy lost. So this is the opposite. This isn't heat required, like in 40, it's heat lost. Heat lost, that's a negative sign, right? When 125 grams of iron cools from 118 degrees Celsius initially to 55 degrees Celsius final. Specific heat of iron, by the way, they would give it to us as 0.452. Q equals MS delta T. So where's the negative sign going to come into play? Well, that comes into play when we do our T final, 55, minus the T initial of 118. That's going to be a negative number, right? So Q equals minus 3559.5. We have to get it into 2 sig figs because of the 55